Hi, this is Scott Wilkinson, host of Home Theater Geeks. In episode 74, I chat with Gene Dolgoff, the inventor of digital projection, and his wonderful work in 3D. So stay tuned.
Netcasts you love.
From people you trust.
This is Twit.
Bandwidth for Home Theater Geeks is provided by Cachefly at CACHEFLY.com.
This is Home Theater Geeks with Scott Wilkinson, recorded July 25th, 2011. Episode 74, 3D Mayhem. This episode of Home Theater Geeks is brought to you by Netflix. Watch thousands of TV episodes and movies streamed to your PC, Mac, or TV instantly. For your free 30-day trial, go to netflix.com/twit. Hey there, Scott Wilkinson here with HomeTheater.com. And today is the first day that we are using a new video system to record the podcasts from Twit's new studio in Petaluma, where they just moved yesterday after months and months of preparation. But you're going to notice that my guest, Gene Dolgoff, is going to look a little strange because the aspect ratio isn't quite right. So I hope you'll forgive us for that. But as Gene says, information is more important than image, which means he's definitely not a politician. Gene Dolgoff, in fact, is a repeat guest, a return guest to our show, having been one of the most requested return guests of any that I've had in the last year and a half. So I'm really happy to welcome him back to the show. Gene, how you doing?
Great. Thanks so much for having me back.
And I'm sorry you look a little stretched out there, but as you said, the information is more important than the image. I happen to agree with you on that, but then again, I'm not a politician either.
Good.
So I wanted to have you back on the show, Gene, because, and before I say that, I want to make sure that everybody knows that those who are tuned into the live stream at live.twit.tv or checked into the chat room at irc.twit.tv can post questions for Gene. I'll be monitoring the chat room, and I'll pass along as many as I can during the show. So, Gene, as I was about to say, the reason that I wanted you back, among many, is that you, in fact, were involved in the development of digital projection right there at the beginning. And I wonder if you would reiterate to our audience how it was that you became involved, what you did in the development of digital projection, and why it's so important.
Great. Thank you. Well, back in the 60s, the only way to see a large picture, a television picture, was with a 3 CRT projector. And there was a red CRT, a green one, and a blue one. And each had a lens in front of it. And they were all focused on a screen, which was in front of the lenses. And you'd put this monstrosity in your living room. And you'd have to align it or pay somebody to align it first. So all 3 images had to be superimposed onto the same screen, and then they all had to be adjusted for linearity, for pincushion and barrel distortion, and it was a pretty complicated task. And if you got it right and then you accidentally kicked it sometime, the whole thing went out of alignment. You had to redo it again. So it's pretty bad. Plus the image was dark because there's only so much light you can pump out of a CRT, small one. And because you were taking the 400 or so lines that the CRT was displaying and blowing them up large, you really saw these lines and the black lines between the lines. So it was not great quality. I decided that I could do much better, and that it would be something that I wanted and that everybody else would want. So I started working on a new idea, which was to use a light valve, a device that was digitally addressed and would modulate the amount of light that went through it. And that way you could put a very bright light behind it, and then you wouldn't have to turn all the lights off to see it. And also, I was working on the design of special optics so that you'd get rid of the the lines and dots and whatever you'd see from a CRT projector. So that was the goal. I started working on it in college in 1968. And finally in 1971, after trying so many different materials that might be used for the light valve, acousto-optic and electro-optic, and I tried water, I tried all kinds of things.
Water?
Oh, yeah. I had a laser beam bouncing off of a container of water, and I had a speaker and then an acoustic transducer putting waves through the water to reflect the light beam in such a way that it scanned. All kinds of things I tried. But finally in late 1970, beginning of 71, I settled on the use of liquid crystals because they could take polarized light and rotate the plane of polarization, and in adding another polarizer, you could modulate the brightness of the light at a very small point, pixel by pixel. And so that was the LCD. And they had just been making LCDs for certain applications, but no video yet. So I designed this thing in 71 finally, and then I had to wait to get my hands on an LCD until 1984.
Wow.
So finally, it was a long wait, and I worked on other things in the meantime, many other things. But finally I got a custom-made LCD from Japan and put together the world's first digital projector, and it happened to be an LCD projector at the time, in April of 1984. And that's how the digital projector started. Then I showed it around to everybody and tried to get funding for it. That took 4 years of showing it around, which is very, I guess, typical. You have an idea, you even have a prototype, but people say, wow, that's great, but when it comes time to put up money, it's not easy to find people to do that.
And
so finally,
who finally did?
In 1988, I found a guy who was friends with the senior director of the Dreyfus Fund, and he brought him over to see the prototype, and he loved it, and he said, this is really going to start a whole new revolution, and I'm in. And he took out his checkbook and he wrote a check for $100,000 right on the spot without a contract, and that started the company going. And within about 3 or 4 months, I had raised another $900,000, and that was our first million. And then very shortly thereafter, we got the government involved, DARPA, and eventually got another $1 million through DARPA. And then in 1990, we went public, and we had private investors and so on. So altogether, we raised over 20 million and started the industry with that.
Now,
so that's the history of it.
Yeah. Now, did other companies like Mitsubishi, Panasonic, so on, then license the technology from you to create a product?
Yes, I licensed Panasonic, Matsushita, Samsung. I worked on products with Radio Shack, with a whole lot of companies. I met with just about every company in consumer electronics in Japan, in Korea, in Taiwan, and a couple of the U.S. Zenith was one of them. Radio Shack was another. Even the company that makes those Avon, not Avon, but those door-to-door products. I'm trying to remember the name.
I get Fuller Brush.
Well, it's not. I don't know. They might have sold that too, but a very big company. It still is a very big company. Anyway, they worked with me on developing the unit. I worked with 3M, so a lot of companies, and at the same time, Texas Instruments was developing this new light valve called the DMD, digital mirror device, and so we started working with them to apply it to a projector as well. And they got funding after us from DARPA. So we were the first ones to get funding for a digital projector technology. That's how it started. Right.
Now, I wanted to talk a little bit about the difference between LCD, which is where you started, and DLP, which is LCD is a transmissive technology. That is, it's a light valve that lets light, more or less light, through each pixel, as opposed to...
Well, let me just say, I'm sorry to interrupt you, but let me say that there are many reflective LCDs as well.
Well, there's LCOS. LCOS is the reflective LCD technology, right?
Well, nowadays that's what's very popular, but there are other LCD technologies that are reflective as well.
Really?
Besides
like
what? In fact, the guys at I'm trying to remember the company now, in the U.S. had developed this reflective LCD. Boy, I can't remember the name of the company.
Well, Epson recently announced something that they call reflective LCD. Is that what you're referring to?
Well, if it's new, it's not what I'm referring to. But
okay,
I mean,
yeah, it's pretty new.
The very start of LCDs, they were reflective, and that was very common.
Huh? I don't think I knew that.
Oh yeah, back right in the 70s, they started making reflective LCDs. So I'm sorry to step on what you were saying.
No,
the
that's
DMD,
fine.
or the DLP is a reflective device, but LCDs are reflective as well. They both are digital devices.
Mm-hmm.
They both modulate light, but in completely different ways. The DLP or DMD has little silicon mirrors that vibrate back and forth, whereas the LCD has a pneumatic liquid crystal that twists throughout a volume of liquid or goop, and it then rotates the plane of polarization of light as it passes through, depending on the electric current applied to it. And so either way, either system can modulate light on a pixel by pixel basis, and each pixel is addressed in a digital fashion.
And the advantage of that, to get back to your very original point of CRT projectors not being particularly bright and not having high resolution, digital projection addresses both of those issues?
Certainly, because you're using an external light source, so you can make it very, very bright.
As opposed to the CRT projectors, which had the light source and the image source essentially being the same.
Yes, the phosphor on the CRT was the light source, and the phosphors can only put out so much light. And if you try to pump more electricity into the phosphors, they start doing something called blooming. So they don't react linearly anymore, and they don't give you a good image rendition. So there's a limitation to how much you can get out of a phosphor. But as long as you're using an external source, you can get tremendous brightness. So that's one of the things.
Right.
Also, the problem with the pixels was very apparent. Once I made the bright projector, the pixels were so noticeable.
Right, exactly.
Neighbor optically, and therefore got rid of the spaces between the pixels.
Ah, interesting.
That was called depixelization, and I got several patents on that as well.
Now, I know that Panasonic uses that in their LCD projectors. I believe they call it smooth screen or something like that. I believe it is an optical expansion of the pixels so that there isn't so much of a screen door effect. But isn't it also true that over the intervening years, the space between the pixels has gotten smaller?
Correct. That's true. And the DLP or DMD device has always had a pretty small space. It's a high fill ratio. And if you go up to the screen and you look at a projection from a DMD or DLP projector, you can still see those lines, but they really are small. So it's become pretty much a non-issue nowadays using either technology. Then the next problem was efficiency. That was the real big problem. How do you get all the light coming out of your light source, your bulb, onto the screen? And that turned out to be a really tough problem. So I had to come up with a lot of different techniques to create higher efficiency in the projector. And some of those technologies and the patents on those technologies are enforced today, in fact.
Can you give us an example of such a technology?
I'll take you through where the losses are and what the solutions are. First of all, you have light coming out of a bulb, whether it's a filament or an arc, and that light is radiating in all directions, so spherically. So the task is to gather all that light and send it straight into your light valve. So in the old days, projectors just had a spherical reflector behind the bulb, and a lot of light was lost vertically, horizontally. So I designed actually a series of different optical systems with mirrors and lenses of different shapes to capture most of the light coming from whatever the light source is. And one of my claims in one of the patents is a system that captures more than 60% of the light coming from a bulb in a projector. That's one of my broad claims.
Now, what was the efficiency of, say, the spherical reflectors that had been used before?
Those were probably 10–20%.
Wow.
A lot of light lost because they didn't care and they didn't know any better. But with a light valve, you have a lot of light being lost in a lot of other places, which I'm about to tell you about. So every lumen matters. So that's why it's important to, at every point, save the lumens.
Sure.
So after you gathered all that light, then if you're using an LCD, you have to polarize it. And polarization eats at least 60% of the light, and usually 70% of the light.
Mm-hmm.
So that was a real problem. And so I came up with the idea of taking the light and splitting it, and taking the two different polarizations that you can get out of that and rotating one of them to match the other one, and then recombining them. So now, instead of using an absorbing polarizer, which eats 70% of the light, we were using a what's called a cube polarizer. It's a dielectric coating that acts like a beam splitter, and half of the light approximately is polarized in one direction, and approximately the other half is polarized the other way. And now you've got two perpendicularly polarized beams, and now by going through some optics that I patented, you combine them into a single beam, all of which has the same polarization. So now you've lost a maximum of about 10% instead of 70% by just that polarization step.
Wow, that's pretty cool.
So that was another important step. Then the next thing was color. To produce color, they put the light through filters, color filters.
Right.
And they're absorptive. So that means if you're approximately using 1/3 of the spectrum for each color, red, green, and blue, you are throwing out 2/3 of the spectrum and 2/3 of the light to get color. So again, here's another 65% loss of light just because you're coloring it.
Mm.
So I developed some techniques where you can color the light without all that loss, for instance, by splitting the light up into a color spectrum and then using physically the different portions of the color spectrum and having that go through the color filters. So essentially, if you're taking the red portion of the color spectrum and putting it through a red color filter, you have very little loss. And the same for green and blue.
So in other words, you're taking the white light from the lamp, say running it conceptually speaking through a prism, right, spreading out the spectrum, and then taking the red portion that's coming off of that prism and running it through the red filter, so you make sure you get the right color of red. And similarly for green and blue.
Exactly. And therefore you're not eating up all that light now in each color filter.
That is extremely cool.
Yeah, thanks. And then the next thing was, because the aperture of each pixel was smaller than, another way to say it is, each pixel had an area around it that had the conductive wires, so you couldn't have light coming through everywhere. That's
Right.
why you had the screen door effect.
Right.
And even though you expanded the image of the pixels so you no longer could see the screen door effect due to my depixelization system, you actually still were having these big spaces between pixels physically, and so light hitting those spaces was lost.
Right.
So I came up with the idea of using a micro lens array, one lens in front of each pixel, to squeeze the light into the pixel hole. So now you're not losing it on the surrounding areas of each pixel. So that was another major improvement. Then the next problem was, you get a light beam coming from that light source, which was spherical. You know, it's in a circular beam now that it comes out of the reflector, and that circular beam is now going to illuminate a rectangular picture. So
you're going to lose a lot of light that way.
Right, you can lose 40% of the light just because you're drawing a rectangle within a circle.
Huh.
Those segments on all four sides that are lost add up to about 40%.
Wow.
So for that, I came up with what I call the light tunnel. It's a quartz rod in the shape of a rectangle, the shape of your light valve. And the light is focused into one end, and then the light bounces around within that rod and reflects on the inner surfaces by total internal reflection.
So it's sort of like fiber optics in a way.
Exactly. It is like a rectangular fiber optic, except that instead of being tiny, it's much bigger. You know, it might be a quarter of an inch high and a little wider. And
well, it's probably a 16 by 9. It's the same aspect ratio as you want your image to be. So it'll be 16 by 9, or in the case of a wide screen, it could be 235:1.
Right. Well, whatever your light valve, like an LCD or a DVD, is, that's the shape of the output face of this light tunnel. And then you take the light coming out of that tunnel and you focus it onto your light valve. So now you're getting a perfectly matched shape of light hitting your light valve, and now you save another 40%.
That's quite incredible.
So going through all those many steps saved, I forgot now, but it's in the patents, tremendous amount, many times increase in efficiency, and makes it practical. And that's what the projectors all use today, to get a large percentage of the light out of a 150-watt bulb, for instance, onto the screen and give you 3,000 lumens or 5,000 lumens. So that's the trick.
Wow. And so all these projectors are using your basic ideas to achieve the amounts of brightness that they do.
Right. I call it brightness enhancement technology.
Wow. Well, I hope they're paying you something for that.
Well, we're working on it.
Okay.
Oh, there's one other technique which I left out, and that was using two bulbs and taking the light from the two bulbs, focusing them together so that they go into the same light valve, and that way you double the brightness once again.
Sure. Now, some very high-end projector companies are doing that, or doing two bulbs, but that costs a lot of money, and so those projectors are going to be pretty expensive.
Well, you know, I don't know what you call expensive. You know, nowadays you can get a projector that does that for about $3,000.
Dual lamp projectors for $3,000 bucks?
Yeah. Panasonic has it. Sony has it.
Oh, I'll have to look into that. I'll have to look into that, definitely.
Yeah, it's fairly common now.
Certainly
the big projectors have it.
Yeah. The other question I wanted to ask you regarding this before we move on is regarding other light sources. You've been talking about white lamps, essentially, spherically radiating lamps. And now, of course, we have LEDs illuminating some projectors. And I know that Mitsubishi makes a rear projector that uses lasers, which certainly don't radiate spherically. They are
Right.
collimated. They go in one direction. So that should solve quite a few of the problems that you have solved in another way. And I'm wondering what you think about LED, first of all, which is being used in front projectors, and lasers, which are so far only being used in rear projectors. And I wonder if they're practical to use in front projectors.
Well, okay. For as far as LEDs go, they are getting more and more efficient and brighter and brighter. I don't think that they give you as much brightness yet as the arc sources do.
Right.
You know, the mercury metal halide bulbs. But for certain applications, I think they work, and certainly they're better in terms of electrical usage. They're much more efficient, last much longer. So there's certainly advantages there. As far as the lasers go, there are some problems with lasers, but certainly front projection with lasers is a no-no. Because if you need enough power to light up a nice sized screen, then you have to have a pretty powerful laser beam. And if you put that out in the user space, then you've got the danger of blinding people if they stare into it. At least if you have it in a rear projection set, you have a diffusion screen, and you have a limitation on how much light comes to a user's eye if he's outside of the set. So it has advantages, but there's drawbacks using lasers. There's speckle that you have to get rid of by certain rotating components or special diffraction components or so on. And there's a power issue. They're not that efficient. They're pretty inefficient lasers.
Oh, I didn't realize that. I thought they were pretty efficient.
Oh no, they are really inefficient. So that's not the best way to go.
Okay, all right. I certainly didn't think about the fact that yeah, if you had lasers shooting out into the user space and somebody looked into the projector, that could be really bad.
Yeah. They won't be watching TV anymore.
No more. Well, listen, thank you so much for that. The next topic that I want to get into with you is 3D, because I know that you've been a big mover in 3D space. Before we do, though, I just want to take a moment to thank our sponsor for this episode, Netflix. Now, everybody knows about Netflix. In fact, I suspect that most of the audience for this show already are subscribers. And so you already know that Netflix delivers movies and TV shows to your home in a variety of ways, on your computer. Most TVs now have Netflix apps. Most Blu-ray players now have Netflix apps. Game consoles of all types, you can get Netflix just about any way you want. And in fact, I just looked at it on a TV I've been reviewing, and it looked pretty darn good. The high-def feed, it's not Blu-ray, but it's pretty darn good. And it's instant gratification, that's for sure. You can watch as many movies as you want, TV episodes, never any late fees or due dates. You just ask for what you want, and it streams down the internet to you. And even better, you can sign up for a free trial at netflix.com/twit. And we certainly thank Netflix for their support of the Twit Network and Home Theater Geeks in particular.
Let me tell you, I have Netflix at home, and it goes right onto my TV, and we think it's great. The resolution is top-notch.
It's quite surprising, actually.
Yeah.
Yeah. Do you have a high-def TV there at home, and I assume you can get down these high-def images. What kind of bandwidth do you have at your house?
Well, we use the FiOS, so
so you got plenty of bandwidth. Yeah. Okay. Well, we've got 5 megabits up and down here at the studio, and I did a little quick measurement and found that the high-def stream was using about 2.75 roughly. So it's not that bad even.
Yeah.
So, so yeah, good. Yeah, see, even my guests all have Netflix. It's a pretty ubiquitous thing. So I guess the ad should really be, go tell your friends about Netflix.
But you can't beat it, and you can't beat it for the price, too.
Yeah, it's absolutely true. It's absolutely true. So the other big thing that you are currently involved in, and have been for a long time, is 3D. And so I wanted to spend some time talking about that, but I first wanted to ask you the question, In my estimation, as I look out into the industry, it seems to me like the 3D craze, the current 3D craze, and there have been several, seems possibly to be waning a bit. Do you see this as well?
Well, not so much waning, but stalling. Let me say something about that. First of all, a lot of people don't like 3D. A lot of people are not interested in 3D. But that's going to change. I guarantee it. And I'll tell you why.
Mm-hmm.
We live in a 3D universe, a 3D world, as far as our perception goes. And we're used to seeing everything around us in 3D and not even think about it. It's reality as we know it. And when we go to the theater or turn on the TV for some entertainment, we're all interested in as much engrossment as we can possibly have in whatever we're watching. So the more real it appears, the more exciting it is. So as we get closer and closer to the real experience that we have in real life, that's going to be more and more preferred, even by the people today that say, oh, I don't like 3D, I'm not interested in. And even the people who don't see 3D, people with one eye, let me tell you, they see reality in a form of 3D that they don't see right now in two-dimensional TV or movies, and of course they don't see it in the 3D movies either.
Yeah, right.
Because they're still just getting the one image.
Right.
But there is a difference when you have no 3D vision and you're looking at reality, and you're looking, or if you're looking at stereoscopic 3D. It's not good, and that's why people who don't see 3D or don't see it well don't like it. But as it approaches the reality experience, people with poor or no 3D vision will start to say, hey, this looks real, even though they don't have normal stereoscopic vision. And so more and more people are going to experience reality-like experiences from it, and therefore it'll become more and more popular. Now, so it'll get there. But right now, it's not, because, first of all, it's only stereoscopic, which means there are two views, and no matter where you move your head, you're not going to be able to have parallax. You can't look around behind things. And there's something called accommodation and convergence, which is very important to our perception of reality. Convergence is how we converge our eyes on different distances that we're looking at, and accommodation is how we change the lenses in our eyes to focus on different distances. And in reality, we are used to converging and focusing at different distances and having an agreement between the muscle tensions of the ocular muscles that swivel the eyes and the muscles that change the lenses. So that gives us a real visceral sense of reality. But when we look at a stereoscopic movie, everything is in focus in one plane, and that's the plane of the screen, whether
right.
it's a movie screen or a TV screen.
Right.
So if objects appear to come closer than the screen or go behind the screen, your eyes will converge on those different places, but your lenses will stay focused on the screen because that's the only place where it's in focus. So your brain sees or feels a discrepancy between those muscle tensions, and it doesn't feel real, and it's sometimes annoying.
This is
actually,
what you probably read. You've probably read Roger Ebert's blog.
Yes.
And
yes.
And this guy Walter Murch, I believe his name is, made this exact argument. And iDoc Mark in the chat room is actually saying the same thing. Accommodation and convergence are what give us stereo vision. And
yeah,
if
that's a big part of it.
Yeah, and if you if there's a disagreement, so to speak, within your brain between where your eyes are focused and where they're converged, this Walter Murch fellow believes that argues that that's what gives people the discomfort. Now, I want to also point out something that Dr. Mom in the chat room is saying, is that further away than about 20 feet, if you're more than 20 feet away from something, she claims that you're not really seeing 3D anymore. Do you agree?
Well, first of all, Dr. Mom might not be a she.
Oh, I happen to know she is.
Oh, okay. But anyway.
No, you're right. You're
right.
The names in the chat room have no necessary correlation between the gender of the person who chose it. But in that particular case, I happen to know it's a she.
Okay. But anyway, I would say more like beyond 30 feet.
Okay.
It's actually surprising how well our eye-brain system can determine things, see 3D, see high resolution that you wouldn't expect we'd be able to see. But yeah, it's true. The close-up stuff is the real important 3D perception. But the stereoscopic way of seeing 3D is very limited, and that's why a lot of people are not happy with it. Plus the fact that the current technologies that are out there are not even good at doing stereoscopic 3D properly.
Why is that?
So that's all. I'll explain it to you in a second.
Okay.
But all this is stalling the success of 3D. But believe me, it's not going to die out, because everybody will want a closer and closer representation of reality, and as it is developed and made available, people are going to start lining up behind it and preferring it. So now to answer why today's stereo is not really doing a good job, there's a few reasons. First of all, the capture part. When you film a 3D movie, for instance, it's important that you do it the right way, and the people who make 3D movie rigs are not making it the right way. And I'm sorry to be insulting, but even Avatar, where they spent a fortune making those camera rigs, is done wrong. And that's why when you watch Avatar, you'll notice from scene to scene, sometimes the 3D is good, sometimes you can't tell it's 3D, it looks flat, and sometimes it even bothers your eyes. The cameras are not designed properly, and they certainly don't work at all zoom distances because the design is wrong. So that's one of the things that I've spent a lot of time designing a new camera system that will capture 3D in such a way that it's consistent, no matter what the zoom or focus distance is, and from scene to scene. So that's something that eventually will get out into the marketplace. So that's the first step. Then the next thing, of course, is how you're displaying it. Actually, how you're transmitting it, and then how you're displaying it. If you're going to a movie theater, they're sending it by satellite and you don't have a problem. But if it's going to be shown on a television, there's a bandwidth problem. And that limits the quality because it limits the amount of information you can send. We've developed a new compression algorithm so that we can get full HD resolution for each eye and full frame rate, 30 frames per second for each eye, all compressed into a single 6 megahertz bandwidth carrier.
So you're talking about broadcast TV. I was about to object and say, wait a minute now, Blu-ray's got plenty of bandwidth for that, but you were really talking about broadcast TV, which currently only gives you half resolution per eye in order to fit in that standard transmission bandwidth.
Exactly, and we have a new compression algorithm so that you can get full resolution per eye and full 30 frames per eye. So that's something that we have patent pending, and we are offering it now. We're trying to make this available to the industry, trying to get it out there so that they can experiment with it, try it, and see that this works. I've already tried it on my computer, and it's indistinguishable from high definition in each eye, and you get full 3D, and you don't need that extra bandwidth. So that's something companies can come to us and we'll talk to them about it.
Wow, I hope they do, because that is one of the problems, of course, with broadcast 3D is the loss of resolution in the over, under, or side-by-side transmission protocols.
Exactly. Then the next problem is the display of the information. And currently we have two different 3D systems: the shutter glass system and the polarizer system.
Wait, before you get to that, and I really want to hear
Sure.
that, but I did get a question in the chat room from Web7599 who asks, how is this algorithm different from MVC, multi-view coding, as it appears on Blu-ray?
Okay. Well, first of all, Blu-ray has no limitation on bandwidth.
Well, it does, but it's not. Practically,
well, I mean,
it's not a problem.
Practically speaking.
Yeah.
And so that you can't take that Blu-ray signal and compress it into the 6 megahertz bandwidth and still get all the data.
Mm-hmm.
That's why the Blu-ray is connected directly to your set. Then you don't have that problem.
Right.
But with our compression algorithm, we are actually sacrificing a little bit more color information, and it doesn't matter because our brains are set up so that color is sensed in a completely different area from luminosity, brightness, details.
Mm-hmm.
So as long as you give full resolution luminance information to the brain, you can cut the chrominance information even further, and we won't notice it.
It's already, the chrominance is already cut pretty far, isn't it?
Yeah. But I found a way to cut it in half, and
wow.
It's still not noticeable.
Wow.
And that, of course, doubles your bandwidth.
Yeah, exactly right. Okay, so
our algorithm does.
Great. So now getting back to the display aspect of things, you said that there were two types of display, and that's certainly true. There's the passive and the active. So please continue with that discussion.
The active uses shutter glasses, and shutter glasses have several problems. One is they're very expensive. They cost $150 each. But besides that, they are flickering on and off, so they do produce some noticeable flicker, especially in the periphery of our eyes. Some people are more sensitive than other people because the rods in our eyes, which sense low light, are designed by evolution to sense the slightest motion, even in the periphery, as a survival mechanism.
Sure.
So we notice that, and so many people are bothered by it. A lot of people notice it, aren't bothered by it, but that's another problem. Another issue is the brightness. The polarizers in the shutter glasses eat up 65% of the light, and then on top of that, you have to close each eye for at least 50% of the time, so that each eye can only see its own image on the screen, and that actually can't be 50% because the hysteresis, the lag between display of one image and the other, causes there to be a time when you see both images when it switches, and that causes ghosting. So to get rid of that, each eye is actually open for less than 50% of the time, so that's cutting out even more than 50% of the light, on top of the 65% you're losing due to the polarizers.
Right, and so in other words, there is a period of time when both lenses are closed.
That's right.
In order to avoid this
to cut
ghosting.
Down the ghosting, exactly right.
Mm-hmm.
So that cuts your brightness down further. So that's another limitation on shutter glasses.
Yeah, Darth Galt in the chat room says, 3D is too dark to watch in the theater, too. I would agree, particularly, I went and saw Thor, I believe, at a commercial cinema that used active glasses. Very strange, very unusual.
Yes.
But it was the dimmest. It was the dimmest picture in a commercial theater I had ever seen. It was horrible.
Exactly. Yep. And that's why. With a television, of course, you can pump the brightness up, and it's only coming out of a small area, so it's more tolerable. But it's still a limitation.
Yeah, exactly.
The passive approach is better in terms of allowing more light to come through. You don't need to shut the light off more than 50% of the time. So now all you have is the polarizer loss. But the drawback, and the glasses are very inexpensive. They're a couple of bucks.
Right.
The drawback is that you have a limited number of pixels on the display screen. TVs are generally made 1920 by 1080, high definition TVs. And so if you're going to wear passive polarized glasses, half of those pixels will be used for one eye and the other half for the other eye.
Right.
So now you have, again, a source of cutting the resolution in half. So even if you had a signal that comes, for instance, from a Blu-ray that doesn't give you half the resolution in the signal, you're going to lose it in the display itself.
Right.
And we have designed a new type of passive display, which we're looking to license to any company that wants it, that gives you full resolution, full high definition resolution in each eye, even though you're using 1920 by 1080 pixels on the screen and you're using passive polarized glasses.
Now, Samsung and Real D have come up with something that fits that description, which is changing the polarization, putting a switching polarizer on the front of the screen and switching that so that each eye sees a full resolution on 1920 by 1080, and it switches back and forth, which is the same way that commercial cinemas show 3D movies with passive glasses. Is your system similar to that or something else?
Right. No, not at all. You're right. The system that they are using is exactly the same as the Real D system that's used in the movie theater. Instead of having the shutters on your glasses in the theater, they put the shutter in front of the projector lens.
Right.
So it's switching back and forth, and then you just can wear the polarized glasses. But with a television, that means that you've got to have a big, fast, high contrast LCD in front of the entire screen.
Right.
So you've got to have an expense that's added onto your TV to be able to switch the polarization back and forth between the two perpendicular polarizations. So that does raise the cost of the set.
Yes.
Our system doesn't do that. Our system uses a new sandwich of retarder material. It's a quarter wave and half wave material arranged in pixels, so that you're able to get sub-pixel polarizations. And then using our compression algorithm, we're able to use a subset of those sub-pixels so that we cut down the color information that's displayed to each eye while leaving the luminance at full high definition for each eye. So there's nothing electronic in our system. There's no switching. It's a passive, totally passive system.
So it wouldn't add to the cost of the TV all that much.
No, it shouldn't add much at all. It's similar to the wave material that's used now. It's just slightly different. So I would say maybe it'll add another $50 or $100 at most. That's not a big deal.
Sure.
Now, there's another drawback to the passive systems that are on the market, and that is there is a limited vertical angle of view.
Yes.
And
that's a good point.
Now, the reason for that is that the polarizing material is on the surface of the LCD. The pixels are inside in the center between the glass plates of the LCD. So there is a parallax error. If you're looking straight on, you're looking through the polarizers and you're looking at the LCD material, everything's fine. But if you stand real close to the set and look down at it, or if you sit on the floor and look up at it, now you're looking at the LCD through a different area of the polarizers, and now you're getting a parallax error. So now you get ghosting and double image and lose your 3D. With our passive system, we have a micro lens array that focuses the light right into the polarizers. So that way there is no parallax error. And so consequently, you can see the correct polarization standing up, sitting on the floor, and you get a wide vertical angle just as you have a wide horizontal angle. And that's patent pending.
Wow. I really look forward to seeing that. I hope, well, I'm sure you have some demo prototypes, and maybe we can get together. I'd love to see that, and then hopefully we'll see it appear in commercial product.
That would be great. We're looking for the companies to license it. So if anybody's listening and you'd like that system, contact us at 3dvision.com.
Well, now we're running a little late today, and we're doing that because we started late because of the switch over to the new studio and the little problems and technical glitches and so on. So I'm just going to ask you one more question about 3D. And that is the future of 3D. And I know you wanted to spend a lot of time on this, and we don't have a lot of time, but I would like to get your hit on, you mentioned that we would eventually see our 3D displays go towards holography. And this is very exciting to me. Of course, I watch Star Trek, at most of our audience probably does, and they know of the holodeck, where you go in and it looks like you're actually in an environment that's holographically generated. I don't imagine we're going to see that anytime soon, but I have seen some prototype holographic displays that were not very impressive. They were like just line drawings or dot drawings. Are you seeing the potential for something better than that in the foreseeable future?
Yes, let me first say that the holodeck was my idea.
What?
And I worked with Gene Roddenberry back in '73, I think it was.
No kidding.
Yeah, I showed him holograms. I taught him all about holography, and I specifically explained to him when he had the first Star Trek, look, this is the future, and the future is going to have holography, and you're not depicting it in the show. That's not right. And so I spent a lot of time brainstorming with him, and we came up with the holodeck idea. I took it further, and I said, not only that, all the displays on the ship should be holographic. He said, but yeah, how are we going to show that on the show? So it just stayed the holodeck the way it is, where you go inside and you see another reality. But yeah, that was my development.
That's incredible. That's incredible. So
anyway,
that's several hundred years in the future. What can we expect to see maybe in our lifetime?
Right. Yeah. The future of 3D movies and television is holography. That is the way it will work. And I really wish we had a lot of time. Maybe we'll do another show on holography if people want it. We could talk all about what holography is, how it works, how it applies not only to television and movies, but how the brain works and how the universe is holographic, and it's all tied together.
Oh man, you're getting into my territory here for sure. Let's just take a few more minutes now. I'm getting a lot of encouragement from the chat room to keep on going. So as long as the folks in the Twit studio don't mind. And sorry, Tom, if we're taking up your time here, but I do want to just get a little bit more into this, if you don't mind. So give us a little bit of a description of what a hologram is and how we might end up seeing it in a commercial display.
All right. As a drop of background, I started making holograms in 1964. The first optical hologram was made in, I think it was November or December of '63. And I got in touch right away with Emmett Leith at the University of Michigan, who made it. And he became a very good friend of mine and sent me all his papers. And I set up the first holographic lab in New York in 1964 in the basement of my apartment building, and started making holograms. It was a lot of fun. I mean, you go down to this dingy basement, and there's this room with these high-powered ion lasers and beams going all over the place and so on. But anyway, so I started working on it then, and I became friendly with Dr. Dennis Gabor, who won the Nobel Prize for it in 1971. I spent a lot of time with him during the late 60s. I spent time with him in England at the university in London, where he was. And he unfortunately died in '73. And in '74, I bought his entire laboratory, which I still have.
Wow.
So holography was really a big part of my life starting in '64. And when I learned how it worked, it just became a revelation to me, because it became obvious to me that that was the most fundamental process in the universe, and it was behind so many other things: how the brain works, how the universe and reality works, and of course how you make three-dimensional images. I'll tell you one little piece of it, and that is A hologram is a recording of an interference pattern. Light rays, when they cross each other, they interfere with each other. And interference means something different than radio interference.
Right. It's just like when you drop two stones in a pool, in a still pool of water, the waves radiate out circularly, and when they meet, they create an interference pattern that you can see. And the hologram is much the same thing.
Yes, it's a recording of that kind of a pattern. But the thing that's interesting to note is that it's a two-dimensional pattern. But that pattern will modify waves that pass through it. So here you have a two-dimensional pattern, but you put a light beam through it, and it causes those light rays to change in such a way that they reconstruct the three-dimensional field of light that existed when the hologram was made. And so now you have reconstructed a three-dimensional wave field from a two-dimensional surface. And that's really very important for two reasons. First of all, for television, because the television surface is a two-dimensional surface. But the room, the environment that you're in, and the reality that you want to experience is three-dimensional. The hologram can take light waves from within the set and reconstruct a volumetric three-dimensional light field, which then will look like reality. As you move your head through it, you'll get different angles of view and different accommodation and convergence, which you don't get with stereoscopic 3D.
Right, exactly.
So that you get the 3D experience that you get in reality. Just a quick aside, this was on TV last night. Back 20 years ago, there was a lecture given by Stephen Hawking about his new revelation about the black holes. And one of the things he said was, when anything goes into a black hole, it's destroyed because the black hole eventually evaporates. And so in physics, what's understood is there's information there. Even if light waves and matter falls into a black hole, the structure that it has is information, and that can't get lost according to the basic laws of physics. So if it's true that it gets eaten by a black hole and the black hole disappears, then the information would be lost. And this made everybody in physics nuts. And in particular,
it'd be a violation of one of the basic laws of physics.
Exactly. Information is not lost, just like you can't destroy matter or energy, just convert from one form to the other. Same with information.
Right.
There was a physicist in California. He was a plumber initially, and he became a physicist. Leonard Susskind. Leonard Susskind is at Stanford, and he was appalled by what Stephen Hawking said. He said, this is not possible. And he said, there's got to be a solution to how this can be true. And he spent 12 years thinking about it. And then finally he thought about holography, and he realized the holographic principle is you can have a two-dimensional surface with an interference pattern on it, and it can generate a three-dimensional field of energy and matter. So he said that must be it. There must be a place, which is called the event horizon, where there is a two-dimensional pattern that represents the information that's reconstructed into 3D in our universe. And nowadays, everybody's seeing the logic of that. And if you think back, since the universe is expanding, if you go back in time and contract the universe into the Big Bang, well, it's like a black hole that the universe started from. So the universe started from a black hole. The information that's here now couldn't have disappeared if you go backwards in time. So it had to be at the event horizon of the Big Bang, and therefore a hologram at the Big Bang generates the three-dimensional universe that we experience right now.
Oh, man. We're getting into some serious philosophy here and some serious physics. It's just up my alley, and unfortunately, we're out of time.
Oh, my.
You know, will you come back and we'll get much more deeply into this, because I could talk about this for hours.
So can I.
Very good. Very good. Then we will definitely have you back. And for now, we just must say goodbye to give way to TNT and the next show on the TWiT network. But for now, I want to thank you so much, Gene Dolgoff, for being on the show and talking about such fascinating things. And I look forward to seeing you on the show again.
Thanks so much. Just let me know.
I sure will. You can contact Gene and read all about his stuff at 3-dvision.com. My online home now, the one home, is hometheater.com, where I'm the online editor. And you can also email me with any questions or comments or suggestions to scott@twit.tv. And you can follow me on Twitter at htgeekscott. Next week, my guest geek is scheduled to be Michael Fremer, the Audiophile's audiophile, and a longtime contributor to Stereophile magazine, one of our sister publications. And I'm sure he's going to have a lot of interesting things to say in the world of audiophilia. So I sure hope you will tune in for that. Until then, geek out.